بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to this course. First of all, my name is Rami Rashad. I'm a new assistant professor here at KFUPM. Before we start, the whole video, the whole course will be recorded. Okay, I'm gonna tell you in the end some stuff if you have any doubts or any concerns about being recorded, if your voice comes into the video and so on. But this recording is completely for your sake. Okay, so I'm gonna tell you inshallah later about it. But for now, completely ignore it. Okay, just feel free to ask as you wish, talk, and yeah, whatever. Okay. I see also here in the screen that also the door is being recorded, so people who come late will always appear in the video. So that's maybe a motivation for you to come early, okay, later on, if you don't want to be recorded. But again, later on that, and inshallah. Okay, for now, let's start. So this is a special topics course, and being a special topics course, again, it's like a placeholder for any new course that we want to try out in the department. So this is a completely new course I'm going to tell you about, inshallah. It's being designed from scratch. I'll tell you more about it, but first let me tell you a little bit about myself. So I graduated. I'm a mechatronics engineer by training. I graduated from the German University in Cairo. I had my bachelor and master's there. I started working in control a little bit, and then started moving into mobile robotics, and then into drones. After my graduation, I joined. Had some teaching experience at the GUC, and then I joined in 2016 ROM, the Robotics and Automation, the Robotics and Mechatronics group in the University of Twente in the Netherlands. I had my PhD there, and then I stayed there for 4 years as a postdoc, and now I'm here. Okay, so this is my second semester here at KFUPM. Hopefully this will not be a disappointing experience for you. So far, my experience here has been very good. This is my first time to teach a graduate level course, so bear with me. Okay, so I'm here learning as much as you in that respect. My research is on aerial robotics, especially on aerial robotic manipulation. So using drones for physical interaction, not just as flying sensors, but to physically interact with the environment. The design of the drones, the modeling of the drones, the control of the drones, all of this is part of the research I'm personally interested in. And more also on robotic manipulation in general, just again with legged robots or with robotic manipulators in general. So these are the branch of stuff I'm interested in. And there are also there are research opportunities available. If you want to learn more and to know more, just get in contact, inshallah. You can also check out my website if you want to look at some of the previous works in that respect. Now for the course. So the SCE 594 is a course, formally it's called the Special Topics in Intelligent Automation and Robotics. However, its real name is Geometric Control of Robotic Systems. And there are 3 aspects of this course that you're going to be seeing, inshallah. The first one is robotics. So this is a course on robotics. This is a course on control, model-based control, not model-free control. There's no learning here. There's no AI. So there's a completely model-based control and geometric control. So geometric control. Hello. Welcome. So geometric control or geometric modeling and control, the geometric approach for the control of robotic system is the whole theme of this course. Okay, so everything we're going to be doing is geometric. And you're going to learn more, inshallah, today throughout the course. What does geometric mean? First, the question is, what kind of robotic systems we'll be focusing on? And these are the type of systems that we're gonna covering in this with the set of tools that you're going to be learning in this course. First are multi-rotor UAVs, multi-rotor aerial vehicles, quadcopters, hexarotors with variable tilt or fixed tilt, and so on. Fixed base manipulators, we're going to be also considering standard robotic manipulators, serial linkage manipulators, and also we're going to be looking at floating base manipulators, which is a big topic, and this is what the whole course is setting up the ground for. for, which is floating base manipulator. When we say floating base, it's compared to a fixed base manipulator or a standard robot arm where its base is just fixed to the ground. A floating base means that the base of the robot is moving, and this can be moving in air, it can be moving on underwater, or it can be moving on the ground. And this includes, and the way it moves or it locomotes on the ground can in different ways. It can be with legs, it can be with wheels, it can be, again, we can use different propellers and so on. You can have different actuation modes underwater and so on and so forth. So you see, we're covering a huge amount of robotic systems. And in order to be able to cover this huge ground, irrespective of where this drone or where this robot is moving or what kind of actuators or what kind of, again, how many degrees of freedom does it have, we need to abstract a lot. And this is where the geometric approach comes in being handy. Let me close the door. And why does the geometric approach? Why is it important? Why is it useful? And why is this the choice to be used? And what kind of tools do you get? What kind of, what's the benefit of it? When we say geometric modeling or geometric mechanics or geometric control, we mean that we're using tools from differential geometry. And differential geometry is a branch of mathematics that focuses on non-Euclidean spaces, and it focuses on coordinate invariants. Okay, what do we mean by non-Euclidean spaces? So first of all, who knows what a Euclidean space is? First of all, Euclidean space. No one. Oh. X, Y, and Z. So R3, you mean? Okay, that's correct. So Rn, what you normally know as Rn. A non-Euclidean space is not Rn. That's simply what it is. The majority of your education, and not just your education, I would say the majority of engineering education at large, I won't say a percentage, but I would say it's just without any proof, it's more than 90%, I would say. It focuses on coordinate-based and Euclidean geometry, okay? And in that respect, we're talking about, when we talk about Euclidean space, we mean Rn. Okay, so in one dimension, this is just the line, you just have a scalar value, scalar state, and you want to control that. Or you have a 2D state, or a 3D state, or 3D space, or in general, Rn, okay? So with this knowledge, again, so if we have a state or we have this is the variable that you're interested in controlling or in designing, you're representing it using Rn, then whatever tools that you're going to be using will be linear algebra. You're going to be using matrices to transform from Rn to another space Rm, and so on, to design controllers and to design state estimation and so on using Rn, okay? This set of tools is very limited, okay? So linear algebra is very limited. And this is where this course comes into place. Why do we need the geometric approach? Why isn't linear algebra the best thing, and why is it not enough for everything? First of all, the configuration space, and we're going to see more on that. What does it mean formally? But the configuration space of most mechanical systems is not Rn. Okay, so whatever mechanical system that you have, okay, most of them that you're interested in, of course, not to mention the more complicated ones like the one that represent like floating base manipulators or complicated robotics, but most, even the simplest one, even the simple pendulum doesn't have an Rn structure. So Rn isn't enough even to model a pendulum. So the configuration space of a pendulum looks like something called S1. It's called a circle. It's a circle. It has a shape of a circle. An n degree of freedom manipulator. So an n degree of a robot arm with n links connected to each other by joints has a configuration space that's looks like a torus, looks like a donut in n dimension. We're going to look at what does that mean later. A planar mobile robot, so just a mobile robot that moves on the ground, has a configuration space that's known as SE2, the special Euclidean group. The multi-rotor aerial vehicle, so a quad rotor, if that's what you're interested in, has a configuration space known as SE3, the special Euclidean group in 3 dimensions. An aerial manipulator has a combination of SE3 with TN, so it's a manipulator on something that flies. And you see all of these different systems, from the most complicated one to the simplest one, they don't have Rn as their configuration space. So linear algebras, between quotes, useless in this setting. Not just for robotics, but even for theoretical physics. And by the way, differential geometry is fundamental for modern theoretical physics, okay? Quantum mechanics, general relativity, and not most, but a lot of the tools that are been developed in differential geometry actually came from the theoretical physics side, come from Einstein, from Poincaré, from Minkowski, and so on. So these are very known scientists in theoretical physics, and then their motivation there is not to do robotics, not to do control, but just to represent, try to describe gravity, try to describe light. And simply the universe itself is not our n, literally. Okay, the universe we're living in is not our n. So at least, even if you're not interested in going outside of Earth, just staying within the Earth's surface is not our n. It's a sphere, okay? And now a question to you. So the shortest distance between any 2 points, okay, between Tokyo and Los Angeles, which is now burned. Okay, but from Tokyo to Los Angeles, what's the shortest distance? Is it a straight line or a curved line? Straight line. Again, in Euclidean space, the shortest distance between any 2 points is a straight line. But in a non-Euclidean, like a non-Euclidean space, the shortest distance is not a straight line. Again, so this is just an example why actually airplanes, if you look at a map, why do airplanes take curved paths? So on the spheres, on the Earth's sphere, this is the shortest path that this airplane is taking to save fuel, and so on. Okay, so, and also even space-time. Okay, so, and space-time, you're familiar with the term space-time, right? From physics. Okay, and it's not space and time. It's not there's no hyphen, there's no space. Space-time is a word, it's one word. Because just to emphasize that the universe we're living in, okay, that's not space, it's not R3, it's not 3 dimensions, plus an extra dimension that's time. It's not a 4-dimensional R4, okay, that we're living in. It's not just that time is flowing by itself and in some direction and space is moving and we can move in 3 dimensions. Space-time is one thing, okay? Space and time are related together on a manifold that's called space-time, okay? So you see, literally, Rn is not everything, okay? So it's very limited starting from mechanics up to theoretical physics. The course that we're going to be, the topics that we're going to be covering in the course are as follows, okay? So the course is divided into 6 topics. The first one is mathematical foundation. So this will be a little bit, I don't know if it will be boring or not, but it will be technically heavy in terms of mathematics. So we need to lay down the foundations for whatever mathematical tools we'll be covering. And we're going to be covering in the first part abstract mathematics. So there will be no robotics, no control, no modeling, just mathematics. Okay, I think I don't remember how much time we're going to be spending there. Okay, but you're going to see in the syllabus, inshallah, on Blackboard. But this part will be a pure mathematics part. Okay, not pure as in pure field of pure mathematics, but it will be more on without any applications. Okay? Forget about robotics. In this part, you need to only relearn, I would say, mathematics or abstract thinking in terms of mathematics. We're going to be covering set theory, linear algebra, group theory, manifold theory, and Lie group theory. We're going to be starting today, inshallah, with set theory in that respect. Then we're going to be looking at rigid body modeling. Okay, if you have just one rigid body, how do we model that? Okay, because the rigid body, just one rigid body, is the building block of all of robotics, right? So a serial linkage, a robot arm is just a group of rigid bodies connected to each other with joints. If you have a mobile robot that's moving around, it's just one rigid body that's moving either on the plane or in the space or under the water and so on. So understanding rigid bodies without talking about robotics is also very important. The kinematics and the dynamics and how to represent a rigid body and its configuration space using the tools that we developed here will be the second topic. Then we're going to be focusing on fixed manipulators, fixed base manipulators. So the fixed base manipulators are just the robot arms, and we're going to be taking these rigid bodies, one rigid body that we had, another rigid body, and connecting them together. This connection will be with the joints. How do we describe the joints with the differential geometric tools that we're going to be developing? Then we're going to be deriving the forward kinematics. Okay, how do we go from all of the different like joint angles or joint degrees of freedom to the movement of the whole robot? How do you describe the dynamics? And again, we're going to look at some advanced stuff on we're going to be covering later. Then we're going to be starting at the midway on the control part. We're going to be starting, there's no control without stability. So whenever we design a controller, before putting it on the real system and just sending it in the wild, we need to make sure theoretically on paper it works. Okay, and by doing that, it's also by mathematics. Again, we're going to be very briefly looking at Lyapunov stability. Anyone familiar with Lyapunov theory of stability? Okay, another course? Did you take in another course? Adaptive control, perfect. Okay, so if you have information on adaptive control, you know how Lyapunov stability is being used. We're going to be using it here briefly. We're going to be looking at PD control. Everything we're going to be doing with the course will be at the level of a PD/PID controller. We're not going to be going more advanced than that. And this is the whole idea of the geometric approach. All of the nonlinearity, all of the more complicated math goes into describing the system, goes into modeling the system. But once you know what is the underlying configuration space, what is the geometry of it, how does it look like, it's not Rn, then the controller becomes very easy. And this is the whole idea, right? We're not going to have pages of a controller. We're going to have very, very simple controllers that are going to be very powerful. This is hopefully what I promise. Okay. Then when talking about the stability and the control, we're going to be looking at the quad rotor dynamics as a case study, or multi-rotor aerial vehicles in general, and we're going to be designing a controller for these systems. Again, so just knowing about rigid body dynamics is enough for you to design a controller for quad rotors, but that's not enough. If you want to talk about fixed base manipulators, you need more advanced controllers. We're going to be looking at motion control and force control. Anyone familiar here with impedance control, the term impedance control? Force control, hybrid force, position control. Okay. So all of these techniques that I mentioned follow under the umbrella of force control. So when I have a robot arm that moves around, this is just motion control, right? Changing the degrees of freedom to have some sort of shape or to go to one place. But robot arms are made to interact with the environment, right? Not just to move from one place to the other. Maybe a mobile robot can do that, but a robot arm needs to interact, needs to not just to pick and place, by the way. It also needs to, I don't know, like write, like draw, needs to grind, it needs to cut, and there's a lot of drill, do screwing and so on. So there's a lot of mechanics and there's a lot of, again, dynamics that goes into there. And we need special controllers for that respect. So this is another also focus of the course. Taking all of this knowledge, now we're going to be going a level up to floating base manipulators. And again, we're going to taking the rigid bodies that we have, and then the robot arms that they have, all of the methods that we learned throughout the course are going to be, again, taking this base and making it fly. And just by doing that, you might think, okay, it's trivial, right? We know how to design a controller for a robot arm that's fixed. We know how to design a controller for a mobile robot that can move. Putting both together is simple, right? Definitely not. Okay. And as again, it starts from the configuration space. The configuration space of a floating base manipulator has a wild geometry. I would say not too wild, but again, it has a very nice geometry that can be exploited and to describe. And you see, just by looking at this geometry, a lot of stuff in designing the controller for this, and there's a lot of dynamics that goes into this kind of system. So this is the most complicated part. You see from the course that they're all connected to each other and they all build on top of the other. Okay? It's good news and bad news. So the good news is that, okay, you're going to build up some knowledge. Okay, so it's not just a random topics that are not connected to each other. There's an exponential curve, hopefully, in gaining some knowledge, because we're going to be talking about the same topics, the same tools, and moving on with them. The bad news is that if you fall at some point, but you're going to carry on. So this is the good news and the bad news. And that's why actually this course is recorded, okay? So this is the reason, okay? Because if you miss any lecture, okay, if you did, for any reason you're not able to come, or if you want to repeat again one of the old lectures, this is why this lecture is recorded. This is an intensive course, okay? And intensive, I mean it's hard, okay? To be honest. This is a graduate level course, not undergraduate, so you need to do a lot of work by yourself. You need to do a lot of studying. This is an advanced applied mathematics course. If you have any problems with mathematics, if you have any problems with robotics, this is not the place for you, okay? If you're interested in robotics, but you're afraid of the mathematics, that's good, no problem, okay? You can welcome, but again, you just need to build up the knowledge. We don't require any prerequisites for this, except for linear algebra, okay? Who here is not familiar with linear algebra? Matrices, vectors. Okay. Another point that's a little bit technical, that this a prerequisite for this course is SCE 507. So the what's it called? Multi-variable linear control. Who did not take this course? 1, 2, 3, 4, 5. You have to check with the graduate committee on how you can register for this course, because again, this is just some again organizational issues. I don't know if you can take it together. I don't know. I don't know if it's not, if it's offered now right now or not. No, the AE department are offering it right now. SCE 507 or something equivalent. Something equivalent. Okay, so you can check whether you can take this equivalent course. Is this the course of Dr. Ali Biladi? Or... Okay, so check whether this is enough that you can take it both together or not. But again, this is just an organizational issue. Of course, you're all welcome to attend, even if you're not taking the course. Everyone is welcome. The course also includes some programming assignments. It's not just math. It's not just again on paper. There's also some programming, and for that we're going to be using MATLAB. So we don't require any again fancy programming languages. Even though I hope later on we can move or at least look at some Python, because everything you can do with MATLAB you can do with Python. It's free. Who here is not familiar with MATLAB at all? Perfect. Okay. These are the textbooks we're going to be using. Okay, you see that the course covers a lot of topics, and they're all set together from different resources. So we're not relying on one textbook, we're relying on several of them. The first one is Modern Robotics. So the one by Modern Robotics by Kevin Lynch and Frank Park. These are big names in robotics. Okay, so this book is on fixed base manipulators, purely on fixed base manipulators. Nothing there is on mobile robotics, no quadrotors, nothing is flying. And it looks on interaction, so it looks on force control and motion control, and it has the geometric nature of this course. It has the same nature. However, I'm not going to be following the course even like with the same notation. We're going to have a different notation for pedagogical reasons. But again, if you understand everything we're doing, you can go back to this course and to this book and hopefully read it and understand it. We're going to have another course on control, purely on geometric control. This is a book by Francesco Bullo and Andrew Luis. This book is another thing I forgot to mention, that this book on the modern robotics, it's not covering the basics of differential geometry. So it just jumps into robotics. And then again, we're going to be introducing the tools and the differential geometric tools as if they are matrices and as if they are vectors. So everything there works with linear algebra. Or I'm not going to take this path. I'm going to start with the theoretical foundation of the differential geometry. This is how this book starts. Okay, so they start by a couple of chapters completely on differential geometry on abstract linear algebra. And again, then it starts to apply this in control. And this is a big book, so this is more involved. This is a more involved book, the Non-Holomorphic Mechanics by Anthony Bloch. So in this book, again, it looks at more complicated systems, again, using differential geometric tools, and it also builds up a little bit with that. The assessment of the course is as follows. We're relying heavily on assignments. Okay, and the quiz here is I only put one quiz here just for you to practice how does the midterm exam look like. But for me, I don't even like the quizzes. Okay, but at least, so we're going to have one quiz right before the midterm, so that you know what to expect. However, the main load is on the assignments and on the self-study of what you're going to be doing. The assignments will be some of them will be programming, some of them will be theoretical. So this is usually the assignments are the most important part. The midterm and the final exam are as less than or equal weight to the assignments. I'm also gonna ask for a group project, so that again you're gonna take these tools that you had and you're gonna implement it on a system either you're interested in your research or you want to practice having something complicated. The project is a group based, so form a group. We're gonna discuss later the logistics of how many people. Probably it will be again depending on how many you are. I think you're about 20, so we're gonna maybe have 5 groups of 4 or something like that. It has to be model-based control, again, so using the tools they're going to be developing. It has to have both motion control and force control, again. And it has to have a complex robotic system. So this is the only requirement that I ask for, not just a simple 2D manipulator, right? Otherwise, the simple 2D manipulator and the 3D are going to have it as an assignment. So you need really to level up the kind of work you're going to be doing. It's completely in simulation. So, and also in MATLAB. So what I want you to practice in this course project is to building everything from scratch. You can use like standard robotics tools like Gazebo and ROS and so on. You're going to spend a lot of time in learning and doing the programming, but you're not going to spend a lot of time into like having a feeling for this mathematical tools, which is the whole what the course is about. That's why, again, we're going to be using MATLAB, building everything from scratch and trying to, again, in the same way that we're going to be developing the course. By the way, you can start with the project, again, along with the course, okay? So whenever we finish the rigid bodies, you can go and, again, work on the on your group project and build it bit by bit, okay? So my advice for you is start to find some group and start to, again, to get familiar with each other. And along the way, inshallah, more will follow in that respect. Your study materials for this course are as follows. First are the video recordings. The whole lectures, everything, inshallah, will be recorded for, again, as I mentioned, for your sake. They will be posted on YouTube, but they're going to be unlisted. So only you, only the people who have the link can watch it. So only you, hopefully, will have the link for that. At the end of the course, it will be made public so that other people can make use of it. And you have the right to be forgotten. And what I mean by that is that if your voice appears in the video and you watch it and you want it to be removed, let me know before I put it public, of course. And if you appear in the video for walking in later and so on, if you want to be removed, just let me know. So you have the right to be forgotten. Feel free. The recording is only, again, don't let it make any pressure on you. And so if you want to be completely anonymous in the course, you have the right for that. Okay? Just let me know. Okay, if you watch a video and you want to say, okay, I appeared in this video and please remove my voice, please remove my face and so on, I'm gonna do it, inshallah. How we're gonna have so after every lecture, the lecture slides will be posted on the Blackboard, inshallah. And I'm gonna post the slides after this lecture, inshallah, on Blackboard. And along with every lecture, there will be some reading material, some selected chapters. I'm going to put the textbooks for you, so you can all have them and check them out if you want. However, I'm going to put also for every lecture selected reading material so that you know for this lecture, this is what I need to read without going through the hassle of browsing through the books. You're going to have the lecture slides also posted on Blackboard. You're going to also need for your studying your personal notes. Okay, the course will have a mix of presentations. So usually I'm going to start with some presentation just to either recap what we covered or to use some new topics or some new ideas conceptually using some slides or figures. But after that, everything will be with pen and paper. Okay, we're going to be using the board and we're going to be writing throughout the course. This is a math course, and in my opinion, this is the only way to learn math. I'm going to be writing, okay, and at the end, again, you can either share the notes that you have or take pictures of whatever I'm going to be writing on the board. But in my opinion, writing bit by bit, everything, as long we go throughout the 30 lectures, inshallah, is the best way to learn, okay? Because you're going to be writing it once with notes and whatever, like comments that were said on the side and so on. There is a chance I might add some lecture notes on that. I don't promise it because it's a lot of work. And this course is being prepared for the first time. Maybe next time, inshallah, there will be a lecture notes where everything being said and written on the board. You're going to have it in written form, but I don't promise that for this first version of the course. Okay. Are you ready? I don't know if you're expecting that we're going to end the class and you're going to go home to have dinner, but this is not how it works. We're going to be using the whole time. Okay, most of the time actually we're going to be exceeding the time. I don't promise that we're going to always keep with the time limit. You see the courses, again, it's very intensive and hopefully, inshallah, you're going to enjoy it. This is not for the faint-hearted. Okay, we're going to be going some point fast, some point slow. In both cases, fasten your seat belts. The first thing we're going to be starting with right away is the set theory. Okay, we're going to be starting immediately now with topic number 1 on the mathematical foundations. Now what I want to introduce is set theory today. Okay, just basic sets. Everything we're going to be seeing here, you're going to be seeing today is you should know about it. If you don't, that will be just, again, a quick introduction. Everything here is intuitive. If you did any calculations before any course, you've seen this before. We're just going to set the floor for what comes next, inshallah. But before that, I want to make an important note. Out of this table there, who saw some of these words before? Set, group, Lie group, Lie algebra, manifold, smooth manifold, Riemannian manifold, vector space. Okay. Lie group. Okay. Vector space. Okay. What else? Any of these words that are not familiar to you at all? Most of them. Good. What else? So you know everything. So you know what a symplectic manifold is? Okay, so we're not talking. Okay. Okay, so the whole idea of this, so each one of these is called a space. You've heard the word space before, right? You've heard the word set and the word space. Usually what a set is, okay, a recurrent theme in mathematics is to try to classify spaces. Okay, we say that this is a vector space and it's different from another space that's called a Lie group or another space that's called a manifold and so on and so forth. Usually all of these sets in mathematics, all of these spaces in mathematics are just some sort of set plus some extra structure. And usually as we go along the ladder here that you see, stuff on the top usually have more structure than stuff on the bottom, okay? And by more structure, we mean that, again, just as the name implies, more structure means that more structure, and that's it. So mathematically, it means that it's not just, it's a very hard abstract concept to describe what's not structured and not unstructured, but being the set being at the lower level here means it's the most unstructured object that you can have. So whenever you're talking about a set, okay, or two sets, then we're talking about the most basic level, okay? We're not assuming that we have any extra structure. This structure can be either some operation, okay, maybe some plus, some minus, some matrix multiplication, some vector product, some dot product, and so on. So these are operations. Or this extra structure can be another set, okay? You can have a set combined with another set, and we say, okay, this gives the first set some extra structure. Along the course, inshallah, this will be clear. But the set theory, whenever we talk about set theory, we mean that this is the most basic level. On top of that, if we add something to the set, for example, if you add something, as we're going to see next time, inshallah, to the set, we can make it into a group. If you add something to the group, or maybe combine two groups together, you can make something called the field. If you take the group and make it, again, make some restrictions on it or make some extra structure, you can make it into a vector space, and so on and so forth. Okay. The word Lie group is famous. Okay. You said you heard it before, right? Where? In which context?
Like SCE2, SCE3.
SE2 is a Lie group. SE3 is a Lie group. Absolutely. Yeah. So SE2 was the configuration space of a planar robot. SE3 is the configuration space of a flying robot, just a quadrotor. And you see here that whenever we're talking about this kind of robotic systems, the configuration space, which is how we describe, mathematically just describe this object, this robot, has the structure of a Lie group. And because it's a Lie group, it has a lot of extra structure that we can use and make use of when designing controllers, when designing a model, when writing a mathematical representation of the system, and so on. Okay. This also means that some groups or some spaces have some structure that other spaces don't have. And this is the most important part. Some operations you can do to some spaces, but not to other ones. Rn, the one that you're familiar with, so Euclidean space, has a lot of structure, okay? It has a lot of things that come with it for free, right? It has a addition, it has multiplication by scalars, it has a vector space structure. You can make it into a manifold. You can make it into a Lie group. Is that correct? I'm not 100% sure. I don't think you can make it into a Lie group. Maybe a basic Lie group. What else? With some vector product, R3, for example, you can make it into a Lie algebra and so on. So you see, the stuff that you're used to have a lot of structure, But whenever we come to the other spaces, they might not have as much structure as this. So we need to make sure that we're not violating the structure of these underlying spaces. This is an abstract statement. Hopefully by the end of the course will be clear. Okay, but for now, this is just recorded. When you go back, inshallah, you should understand what this means when we look at these different spaces, inshallah. We started at 5:20, right? So we have until 6:35. Okay, perfect. Okay, so we're on time now. Okay, before we start, okay, let's see. So this is the part where we start to write, but before that, any questions? No questions?
Could you please give us some example about this set or structure or manifold?
Right now. Sets will be right now. Examples on sets and everything will be right now, inshallah. Manifolds later.
Steve, even though you didn't mention it as a prerequisite, but having a background in robotics, something like the forward and reverse kinematics, is it something required?
No, not at all. Okay, so okay, something about this line, this course again will build on the same notation and everything we're going to be starting within this mathematical foundation. Okay, people actually who have some knowledge on other topics or on the stuff that we're going to be discussing will find it even harder than the ones that don't. Okay, because it's much harder to unlearn than to learn. Okay. So, okay, if you're very good with, for example, with linear algebra and you've lived your life and you love matrices, you're going to hate them at the end of the course, okay? And it will be very hard to unlearn them. If you come with an empty mind, everything will be nice. So actually having that's why I said I don't assume any background other than just some practice with linear algebra so that when you do matrix multiplication or you take, again, you do eigenvectors or eigenvalues of, again, with big matrices, 6x6 matrices, you don't get scared. That's just the reason. Okay. Other concerns or questions? There's no intelligence at all. Yeah, the intelligence maybe is maybe me trying to do all of that stuff, but it's natural intelligence. There's no artificial intelligence in that. Okay. This is a special topics course. So again, as I mentioned, we just leave it open in that sense. So it's just a placeholder course. Okay, because whenever we try this course for, again, maybe several like semesters, inshallah, after that it becomes a standalone course and the special topics becomes empty so that someone else might use. Okay, and also there's also a chance that it's not offered again. Okay, so again, someone else takes over this special topics. So this is just an organizational issue. Any other questions? Okay, so now let's the other question is it? Okay. Okay, so let's start by set theory. Okay. First, the first thing we're going to be discussing is sets and some set notation. So this is the first section here. How good is this writing appearing on the video? I don't know. Okay, so don't rely 100% on the video. The video, maybe again, you can use it as if you miss the lecture, so you don't have any other choice. But for the writing, I really suggest, again, as I mentioned, you either write or to hire someone or to pay money for some of the intelligent, like some of the hardworking students here that are writing. Here, but I'm gonna be moving a lot in the along, maybe, I don't know. Let's try it. Okay, see. First of all, what is a set? Okay, so intuitively, you all know what a set is, right? So if I give you a set, it's a collection of elements. Okay? A set, mathematically speaking, doesn't even have to be the same elements, right? So then they can be different elements together. So this is what it means intuitively. When we say an element of X, so if X is an element of a set S, usually we use this symbol that we say that X lives or belongs to or is in S. Okay, so this is just the notation that we usually use. And what this means is that S here can be some sort of collection of sets. So S can be a collection of elements and only one of them here is called X. So you can have X and Y and Z and so on, just different names for different items. Okay, so this is what a set is, theoretically. Formally, actually, this is very intuitive, okay? So that's it. You don't need to know any more information. However, to formally say what a set is, we can take, I think, about 2 or 3 hours just to formulate it properly. And whoever is interested can look at, I'm going to send you some supplementary material on Blackboard for some video lectures if you're interested on that. But this, what a set is usually postulated. It's built on axioms, and it's something called an axiomatic set theory. And it has the name of Zermelo-Frankel axioms of set theory. Okay, so again, if you ever see that, what is axiomatic set theory, it's just some people spend a lot of time just trying to formulate what a set is and what this epsilon is. Okay, for now, we're just gonna jump. Okay, we're gonna have a head start. This is just a set, and this is an element of this set, and this is how we write it. Okay, if you have like another set that's inside of the first one, for example, A, then we would use the notation, this notation. So when we say that A is a subset of S, we're going to be using this notation like this. It's also possible that we can write it both right ways. Okay, you're going to be getting used to writing mathematics in terms of in text. Okay, so at some points we might say that S, for example, have another element that's Y that also belongs to S, and another element, another subset phi B, for example, that also is a subset of S. So again, so this symbol here can be used in both ways, either from left to right or from right to left. It means the same thing. Okay, this is just for to have the syntax clear. Usually when we define, how do we define subsets? Sometimes, many cases, we define subsets by taking the bigger set, the superset, and trying to impose some conditions on the elements that are inside. Okay, so usually when we define a subset, we would use this terminology. So we'd have that, we write it like this, that A is defined as, and we would write that okay. So you read this mathematical sentence as follows. You say that A, the subset A, is defined as, so this is the notation we're going to be using for is defined as another set. So A is defined as a set, and this set contains all elements X that belong in the bigger set S. Okay, so from this immediately implies that A is a subset of S. Okay, so A is in the collection or is the set of all elements X. Okay, that satisfies some sort of conditions, and we use this notation. So again, so this vertical bar here to say that such that. Right, so it's the set of all elements X that belong to S such that some conditions hold on X. Okay, so this is the notation that we're going to be using to define subsets. If we have two sets, we can combine them to make new ones. So if I give you a set A and a set B, you can combine them in different ways. The first way to combine them is to take the Cartesian product of both of these. Okay, so the Cartesian product is defined such that, so we define it also in this way. So it's the, okay, I'm not going to define it as a subset of something else, otherwise we're going to make it more complicated. But for simplicity, this is defined as the set of all pairs X and Y. Okay, so these are ordered tuples. So X comma Y is different from Y comma X. Okay, so X comma Y is an ordered pair, and this pair lives in this space, this new space, where X lives in the first space in A, and Y lives in the second space B. Okay, so with this notation, we took two sets and we define the Cartesian product of them. Okay. We can also define the n-fold Cartesian product, right? So if I give you one set, S, and I write S power n, okay? What I mean by that is that I mean this is S, this is the Cartesian product of S with S with S with S n times, okay? And usually we write this like this. So this is defined as S times S n times. Okay. Another way of combining different sets together is by the union, right? So when I say I have A union B, okay, so for example, this is A and this is another set B, okay? So the union of them is, okay, all of these elements that are in either in A or in B, okay? So the union includes all of the elements that are either in A or in B. What is the set that has elements that should be both in A and B? What's it called? Intersection, exactly. So the intersection, okay, which has this symbol, okay, between these two sets A and B, means that elements, this is a new set that has elements that should be both in A and in B, okay? We're going to be using this notation, okay, phi, okay, but it's not just it's not the standard phi that like we use for angles, for example, but this is more of like a circle with some backslash. So this phi, we're going to be using it to denote the empty set. So we denote by this the empty set. Okay. What is the empty set? The set that has no elements. Exactly. So this is just what the empty set means. Okay. If we have A and B, okay, if we have a set here that's called A union B, okay, so it's the union of A and B. And at the same time, we have that the intersection of the same A and B is actually empty. What does this mean? There's nothing common between them, and you want to combine both of these together, right? You want to have the set, okay? So it's not like this picture here, right? Because this picture has some sort of intersection in between. Okay? But if I have A alone and B alone, and I just want to combine them together, by the way, they don't need to be connected. The term connectedness is not relevant here. Okay? We cannot talk about connectedness if we're talking about sets, so this is important to note. But again, just visually, again, they can be different, okay? They can have no intersection, they can not be touching each other, whatever. So S can be the union, if S is the union of both of these two, and there is no intersection between these, or in other words, the intersection of A and B as sets is empty, then we call S to be the disjoint union of sets A and B. All of these are just terminology, okay? Just we're setting the ground because we're going to be using all of these later on, inshallah. Okay?
Joint union, which means these two conditions
together.
Be satisfied?
Together, exactly. Yes. It's a set. It's a union of A and B, but it's not any normal union. Okay? It has another extra condition. Okay? That A and B should not have any intersection between them. Okay? Or there are no elements that are both in A and in B. Okay? Let's look at some examples. Should I wipe this? Anyone needs it? Wipe? Okay. Let's try Yusuf's advice. Let's try to store it.
Here.
Where? This one? That's maybe a better idea. Add, yeah, that's good. Perfect. Then we can see how to save it. Perfect. Okay, thanks a lot. Let's look at some examples. Okay, the set of integer numbers is called Z. Okay, if you have integer numbers, okay, then we call this Z. What does the C, what does the Z have inside of it? Integer numbers. 1, 2, 3. Also what? -1. Does it have the 0? Yes, it has also 0, right? So we have from minus, again, I don't know, 4, 3, and so on, up to 4, including also the 0 and blah, 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 okay? Up to, does it have any end? Is it finite? It's infinite, right? Can you count it? That's something to look at it at your own pace, okay? So we can call a set either finite or infinite, okay? Intuitively, you know what that means, right? If we have limited, if we can count the number of elements into it, okay? We can formulate it more properly, but again, this is just intuitively what it is. But you can have something that's infinite and you can count it, and you can have something that's infinite and you cannot count. These are called countable countable infinite sets or uncountable infinite sets. That's for you to look up if you're interested in that. But we're not interested in this description here.
Means the number of the elements in the set.
I'll give you an example of something that's not countable. Okay, maybe at the end. Okay, so this is the Z. The natural numbers we denote by n. The natural numbers include what? Does it include the 0? So the natural numbers, they include what? They include the 1, 2, yeah, up to something that's large. Does it include the 0? No, it doesn't include the 0. Okay. If we take the union of n and we take, let's write it like this, and we take the 0, okay, what do we get? We get a new set, right? So we took two sets, two small ones, and we wrote it like this. So we usually denote this to be the Z plus, okay? So this is the Z that has the 0, the natural numbers, and the negative natural numbers. You can think of it this way. So this is the integer numbers. The natural numbers, again, is what you count. But the positive integers is this space. Okay, sorry, it's this set. Does anyone, is there anything here that bothers someone notationally? Notationally. So n is a what? Is a set, right? What about the 0? Is it a set? It's an element, right? So if I write, for example, if I ask you a question, does 0 belong to n? Do you say true or false? It's false, right? Does 0 belong to Z? That's true, right? So how do we differentiate between one element and a set? Usually we use this notation, right? We just say that I'm thinking about the 0 as a set. It's a set of one element, but I just write it this way, okay? So that there is no contradiction. This is something we're going to be focusing on a lot, that whenever we introduce some notation, we make sure that there's no contradiction with other things that we have. We will try, and for that, we're going to be maybe making the notation a little bit as an overkill. Maybe you know what it means. Maybe it's just writing extra stuff. Maybe this is, again, if you read something mathematical, like context, mathematical text, or a monograph, you find it's heavy, but it's just to be precise, okay? Just so that we don't mix a 0 as a set or 0 as an element, okay? And so we're going to be trying to be precise, not very much, because this will, again, take us a lot of lectures just to build it up formally. But again, that's as much as possible, we're going to be trying to be precise in that respect. Yeah, the question?
Numbers doesn't belong to n,
No,
right?
no.
Why you told us now there is a condition, we can say something x belongs to set and condition, right?
Yes.
Why, rather than taking the z and the n, we talked in the previous slide, for example, x belongs to set.
Yeah.
The condition x greater than.
Yeah, okay, yeah, I see. Okay, I see what I mean. So this is how we define sets, right? You can either define sets by enumerating the elements that are inside, just like this. So I say that the set has 0, 1, 2, 3, 4, 5, up to infinity, I write it explicitly. Or I can say that the set is defined as a subset of another set. These are two different ways to define a set. Okay, so here I'm writing it again because it's intuitive, you know what it means. Okay, I'm just enumerating them. Okay, again, of course, I'm not writing all of them. But you can logically add, you can fill in the dots easily, right? Okay, does that answer your question? Okay, any other questions? Okay. Okay, another set. The set of real numbers is called R. So this is the set of real numbers, you know. Okay. Can you count the number of elements in R? Yes, sure.
Natural numbers leaving zero, right?
Natural numbers don't include the zero. Yes. Yes.
Should we give the natural numbers again?
Yes. Yeah. It's like taking the natural numbers and adding to it the zero. Positive Z. Okay. You can also say that the positive Z, which is included here in the Z, by the way, right? Yeah. So it's a subset of Z, right? So you all know what the real numbers are, right? This diagram maybe will summarize this whole picture, right? So usually we have that the complex numbers are, again, as a superset for the real numbers. The real numbers are a superset for the rational numbers, Q. You know what rational numbers are, right? Rational numbers are numbers that you can write as the fraction of two what? Two integers, right? Two integers or two natural numbers. So you can write it as a fraction divided by zero. Two natural numbers, right? Natural numbers are these. Integers have the zero, right? Cannot divide by zero, so we need to pick it out, right? So this is being precise. Of course, everything is 1, 0, and 2 for you, but when we talk about mathematics, we need, if we choose a set, we need to be very precise that what we're saying holds for all elements in that set. Okay? We can divide by negative numbers. That's okay. You can divide by negative numbers, but you cannot divide by zero. So that's the Q. You have the Z inside, and the smallest one is the N. Okay. So N is a subset of the Z is a subset of the Q is a subset of the R is a subset of complex numbers. Okay. And of course, you know complex numbers, right? So it's the A plus JB, right? So why is this subset of it? Because we just set the J part to be zero, right? Just look at the real part. This is exactly what we say, right? There's the real part and there's the imaginary part. Both of them together combined, but we make them to complex numbers and so on. Okay. This is our sets, of course. Another interesting set is S1. Maybe let's write it. Maybe let's go to another board. So another example of a set is S1, which is the circle, right? How do we define a circle? So S1 is intuitively what a circle is in R2. So if this is some R and this is another R, okay? So this is the set that we call S1. It's just what you call a circle, right? It's only the surface of the circle. It's not, doesn't include it doesn't have anything inside. So it's not a disk. It's just the circle of this, the surface of the circle. Okay, so this set is defined as follows. So S1 is defined as all of the elements XY that belong to R2 such that X squared plus Y squared is equal to 1. So this is how we define a circle, right? Okay. And we can generalize this to an N sphere. This is the circle is, by the way, is also called the one sphere. Okay. And you can see that we can generalize this to N dimensions, right? So a one sphere is just the circle. A two sphere is what we in language, in English, we call a sphere, right? And but you can like extrapolate that to N dimensions, right? A three sphere and an N sphere and so on. So an N sphere usually will have this notation. It's defined as follows. It's all of the elements x1 up to xn that live in R n plus 1, such that the summation of all of these xi's, the square of it, from where I goes from 1 up to n is equal to 1. So this is how we define this set. Okay. So this set, again, is known as the n sphere. And of course, the 2 sphere, you would, again, it's just what you would imagine in 3-dimensional, something like this, right? Something that, again, if you're a point on this sphere, you can either go in this direction or in this direction. This is how you'd imagine it. Just like the surface of the Earth. Sorry? Yeah. Let's see. And because this should be n plus 1. You're right. Yeah.
So now this 2n equals S1 multiplied by 2SN, right?
Sorry, again, could you?
This slide.
Yeah.
You said Sn equal S1 multiplied to Sn.
Very good, very good. Okay, very good.
How x squared plus y squared multiplies many times will equal this.
Very good question. This is something that we're going to be seeing a lot, okay? Do not mix something, especially in the notation side, that was said in this context with something that was said in another context. The S that we're talking about here is called the set that's called the n sphere, and we're represented by this symbol, right? The other one that you were mentioning is a completely different context. If you remember, if you go back, you're going to say that, okay, I'm going to put it in a box here. Like I said that assume or let S be a set, okay? And we said that S power n, which is the Cartesian product of S times S times S n times, is defined like this. So you see here, these are different sets. Same notation, but not different sets. Just like saying, okay, I'm going to move in this direction, I'm going to call it X, okay? And someone in another room is going to move in that another direction and is going to also call it X. So the symbol is the same, we have different context. It's a set. But the symbol is the same, but these are different sets. Naturally, these are different sets. If I change here the A, this to be A, nothing will change here. Okay?
But this is general equation.
This is just the definition. This is very important. It's a definition. I just say that whenever you see this, in this context, this is what it means.
For any context, the block.
This is again. This is a part where we have we're using an abusive notation. Okay, this will happen not a lot. Okay, but again, at some point, it's inevitable that we're going to have. Again, we cannot introduce so many variables or so many ways to define the same thing. That's what it means. Okay, so if I tell you, you should ask the question as follows. If I tell you S power n, you should be asking, what is this set? Okay, if it's the Cartesian product of S times, then you would define it like this. So how it looks like here. So again, let's Sn, if it's the Cartesian product of S, then an element here will have something like this, x1 up to xn. I'm not going to write it like this. An element x1 up to xn, yeah, lives in Sn slash an slash rn. Okay, you see, I'm just taking ordered pairs, and I'm gonna stacking them naturally. Just like when you write a vector, right? You take first variable and you put below the second variable and the third variable and so on. You just stack them together. You make them into an ordered pair. Okay? So Rn looks something like this, but this is different, right? You see? It's just notation. It's just definition. If we say here that Sn is defined like this, forget about anything else that was defined, even if it's the same A, right? For example, if I tell you V is a set, and next lecture I tell you V is a vector space, does it matter with you? You see? Different things. Same symbols, different things. Okay? don't hang up too much on the symbols, okay? That's why we're going to be using the symbols all over the place. I might call, we try as much as possible to make it clear, okay? But for example, something that's capital can be a vector, something that's small can be a matrix, and so on. Maybe you're used to having everything that's capital a matrix, everything that's small and bold to be a vector. Don't be hung up on the notation. In every context, in every paragraph that you're reading, always ask, what's the nature of this variable and this symbol that we're talking about, okay? This is important, okay? Very good question, very good comment. Is that clear for everyone? Okay, perfect. Okay, okay, last example. We're gonna have another set of something that you're also used to. We're gonna call this set GLN, R. It's the name of the set, you see? It's just the name. We call it with this. It's not a function that takes N and R and spits out something. It's just the name of a set, okay? We're gonna be defining this set as all N by N matrices, okay? And this is the first time we're going to be talking about matrices. And matrices are just a way of representing some N square numbers, okay? So if I give you N square numbers, so I give you x1 up to x4, for example, x1, x2, x3, and x4, you can write them as a matrix like this. As a set, it doesn't matter. As a set, it doesn't matter. It's just writing numbers differently. Instead of putting them after each other, vertically or horizontally, I can put them next to each other. It doesn't make any difference. As sets, you see, we're at the lowest level of structure. This doesn't have any matrix multiplication, doesn't have any addition and multiplication, nothing. Okay, we're not talking about vector spaces here. We're not talking about determinants and traces and so on. There's no structure. At sets, this is the same as this one. I just can write them differently. Sorry? The order here is important, yes, because when we talk about Rn, in this case, for example, the order matters, okay? If I tell you X, Y, and Z, it matters which direction, because X is the first direction, Y is the second direction, Z is the third direction. Okay. So this set that looks like GLNR is defined as all matrices that we can write like this or like this, it doesn't matter, such that their determinant is not equal to 0. So what is this the set of? Any element in here. What does it satisfy from your knowledge about linear algebra? Non-singular, right? What? No. No column vectors, nothing. Determinant, if I give you some numbers, can you define determinant? Yeah. So x1 multiplied by x4 minus x2, right, multiplied by x3. That's it. Just the definition. So you see it's on the numbers, right? There's no column vectors. There isn't anything. There isn't even the word vectors. Okay? Just some operation on the numbers that make up the M. If it's not 0, I call this the set of invertible matrices, right? These are just the set of invertible matrices. And these are what is known as the general linear I should say group here, but I'm not going to say group. Okay, this is known as the general linear group, but we didn't say what a group is. So I'm just going to say it's the set of invertible matrices. Forget about this general linear group. Later on, you're going to see it, inshallah. So this is just the set of invertible matrices. Okay. Any matrix in here, if you pick up any matrix from this set, it has what? A determinant that's not equal to 0. You can invert it, and so on. Okay, that's it. That's it for now. So what you, just as a recap, so this will be how the course will go on, inshallah. We're going to always start with some slides, inshallah. Most of the time, inshallah, we're going to be starting with some slides, just to recap what was covered, just to give you an idea about what to expect in this class, but most of the time we'll be going to be writing things like this. What we cover today is sets. This is the most basic level. Okay, so you see now again. Maybe I don't know. You got a feeling for that or not, but not everything you can do with every object, right? You need to ask what is the nature of this object we're talking about, right? Is it it has a vector space structure? Is it a vector? Is it a group element? Is it a point on a manifold? Is it just a set with no structure and so on? This will be clear, inshallah, in the next lectures, inshallah. We're gonna, again, as I mentioned, we're gonna be building up on every lecture. Okay, so there's maybe I think 1 or 2 lectures in the middle that are just as an aside that you can miss, or you can just, it doesn't require, you don't require it for moving on, but everything from here moves on. Okay, we need it, so study. Okay, now, or just when you finish. Okay, just after Aisha. Okay, so any questions? Questions on that? No questions. Okay, thank you very much. See you inshallah on Tuesday, inshallah.